So let's look at some of the examples of what we have discussed in class. So let me start with something very simple, just a bit more practice of what we did. Find limit So if you have something like that and this is becoming 0, so you are involving a division by 0, then you want to get rid of it. So the first idea is to factorize it. So always try to factorize the numerator. If there is a 0 in the denominator. Just as an example, if I want to factorize it, what I can do, it's a quadratic function. Look for the two roots. Since it's quadratic. So it will have two roots. And for the quadratic functions, they are actually very easy to find because you can just use the quadratic formula. And if I use this, I get -1 this and 2. So that gives me this root and this root. So 2 and -3. This means that this thing is equal to x minus 2 and x plus 3. That's the factorization because of these two roots. So therefore, this limit is equal to this limit because I just factorized. That's the same function as what you have in the numerator. And since in the limits, you are never at that point, so this is equal to the limit of the function which you get after canceling these two factors. So you get 5. Let's look at another example. Let's look at this. Limit x going to -6, 2x plus 12 over x plus 6. So since you have this absolute value, function, and its behavior, you know, it's not that obvious to see its behavior. So in this case, best strategy is to find the right-handed and left-handed limits separately. If the limit exists, then the right and left limits do exist and they're equal. So this we can always do, but it doesn't buy us, many a times it doesn't buy us much. But in this case, it helps in analyzing the situation a bit better when you have a piecewise defined function around that limit. So I can check this, the right hand limit first. So this, since my x value which I'm putting is bigger than -6 and x plus 6 is equal to x plus 6 if x is bigger than -6. Therefore, this is equal to now again, if I put x is equal to -6, I'm having a division by 0, but since it's very easy to factorize it, I can immediately see that this is what I get for the right hand limit. While if I find the left hand limit, then when x is less than -6, then this guy is equal to minus of x minus 6. That's the very definition. It was a plus. So I get this gives me -2. So what I have is limit x going to -6 minus of this function. Right hand limit is not equal to left hand limit. Therefore, limit does not exist. Now I can, let's take another example. So suppose the function is this. And we want to find right hand and left hand limit. Right and left limits. So when I do that, for example, if I start with the right hand limit, well, let me start with the left hand. 0 plus. Then I have now x is never equal to 0. So these two factors are same. So they cancel to give you a 0. And the limit of a constant is just that constant. So for the right hand limit, you get a 0. Now if I look at the left hand limit, So for this, you get a 1 over minus x. So you get 2 over x. Now in this case, if I put x is equal to 0, the downstairs limit doesn't exist and there's nothing upstairs to cancel it. And one can prove that limit does not exist. It does not exist, but it does not exist in a very special way, which we say that it goes to infinity. That we will discuss next time. But for now, you can say limit does not exist. So it's possible, like in this example, that the right hand limit exists, but the left hand does not. Now, let's take this example. So suppose you are given this function f of x is x if x is less than 1. It's equal to 3 if x is equal to 1, is equal to 2 minus x square if x is bigger than 1 but less than or equal to 2, and is equal to x minus 3 if x is bigger than 2. So this function is defined for the whole range of the real line. That's its domain. And we want to find all these limits. Find limits if they exist. So you want right hand limit at 1, left hand limit at 1, and the limit at 1. Similarly at 2. Right hand and left hand limits and the limit at 1 and 2. So it would be a bit helpful if I draw its graph. And if I draw the graph, so let's count each box as a 1, or maybe 2 boxes as 1, 1, 2, 2. Let's count 2 boxes as 1. So this is 1, and this is 2. This is 1, this is 2, minus 1, and minus 2. So if I look at the function for x less than 1, it's just the 45-degree line because it's just the x. In this range is this. At x is equal to 1 is 3. So it goes up here. I have just marked this point. And for between x1 and 2, it's a 2 minus x square. So it's a parabola, x square, which is inverted. So it's going downwards like that. And then it's shifted upwards by 2 points. So it starts like this. But since it doesn't have this value, so I don't have to draw this. It meets it here. It starts from here. Because at x is equal to 1, if I put this value here, I get the answer 1. So starts from here. And at x is equal to 2, it gives me 2 minus 4, a 2. So it's like a parabola going like this. I shouldn't draw it like a line. Let me try to make it a bit more. Yeah, that's how it looks like. And this is until it reaches 2. Then above 2, it's again a 45-degree line because I have this graph. But it starts at x is equal to, right after 2, it's starting at -1. So from here, and then this is this line. So that's the graph of this function. Now it's pretty easy looking at this graph to find these limits. It also gives us the idea, what do those limits mean? So limit x going to 1 minus f of x, you're approaching these values from the left. Never touch the 1. But in the region when you are below 1, your function is just x. And in that region, you can just plug in the value of 1, and that will be the limit because it's just a polynomial. X going to 1 minus x, I should say just 1. So this is just 1. And one can look at it in the graph that you're approaching this point. And it doesn't matter that the function's value is 3 over here. And if I look at the right-hand limit, again, I have this value on the right-hand side. Right after this, I have to just look at the close enough interval near this point. So in that interval, the value is, the form is 2 minus x square. And since again it's a polynomial, so I can just put in the value and I get 1. Which is obvious from the graph as well, because you are, if you come from the right or you come from the left, you are meeting at this point. Value of the function is approaching 1. Although the function's own value is 3 over there, but that doesn't matter. The approach from the right and left is to the 1. So since limit 1 plus is equal to limit 1 minus is equal to 1, since they are equal, hence we can say that the limit of this function at x is equal to 1 is 1. However, if I look at this limit, left-hand limit at 2, then I see that I'm approaching this value. You can compute it from the algebraic expression as well, but it's just visible from the graph. It's -2, while the right-hand limit, because the value at that point doesn't matter. Looking at the approach, from the right-hand side, you are approaching -1. Therefore, limit limit does not exist. So it often happens when the right hand and left hand limits do not agree. Well, it always happens. If they do not agree, then you have a gap, kind of a jump in your graph. Now let's look at a slightly complicated example. So suppose you are given that limit x going to 1. Well, let me write it this way. Given that limit is 10. Find limit x going to 1 of f of x. Now, I see over here that if I try to use the quotient rule of the limit, that the limit of these two functions will be equal to, if I find the limits of the two separate functions and then divide them, then I have a problem. There's a 0 coming in. On the other hand, the total limit exists. So this implies, since limit does not exist, we should write while limit exists. That means I should write this function containing this vector. That you can always do. So define a function g of x such that you just define it. And there's nothing, this definition is well posed because g of x, according to this definition, is just this function, which is well defined for x not equal to 1. But in computing the limits, we don't care what happens at that point. So this is a completely well-defined normal function. And I got this idea because I want to cancel this point, x minus 1. So then limit of f of x minus 8 over x minus 1 would be equal to, because these two functions are equal over here, away from x is equal to 1. So it's equal to x minus 1 g of x over x minus 1. And we know that we are given that it's equal to 10. 10 or was it 8? 10. But since I'm not at 1, this also implies that I can cancel. So that means that the function which I defined, its limit has to be equal to 10 as well. But since x minus 1, g of x is equal to f of x minus 8 when x is not equal to 1, the limits must be equal because they are equal when x is not equal to 1. This implies and that means this limit can be computed by finding these limits. And by the product rule, this is equal to this. This we just found that this is 10. And this we can find by plugging in because it's just a polynomial and nothing blows up at x is equal to 1. So this is 0. So this limit is 0. But I can use the sum law over here is 0. And this limit, as always, is just 8. So I have found my limit. Let's consider another similar problem. So suppose you are given and you want to find f of x. So again, since you know that the limit exists, so you write define it this way. Then this we know that it is equal to 5. But from here, I can conclude, since x is cancelled, that the limit of g of x is 5. This implies the limit f of x because they are equal when x is not equal to 0. So this is just 0 times 5. So 0. Limit of f of x is 0. What about limit of in this case, I can write f of x over x is equal to x h of x, then limit is equal to the given 5. That means is this. So you got a 0 and a finite number, so 0. So if you look at this pattern, we used simple rules of limit. But what we can see over here, that when I had a division by 0, then to get a finite answer, I always needed some 0 upstairs, a limit which had a 0 upstairs. And actually, even this had to be 0. This limit had to be 0, because I could write this function as this. And since I'm getting a 0, this is approaching to 0. So this guy also should approach to 0 if I'm going to get a finite number. This is just a pattern I'm finding. Same thing happened over here. At the limit point, I was getting this limit going to 0. So this beta had gone to 0 to give me a finite number. And that could have gone to 0 only if f of x was 8. And that's what we found. This is a general rule. And by the way I have done it, you can argue by making it a formal argument in general that if the lower, if you have a quotient, and if it exists while is 0, then only possible then the upper limit also goes to 0. You can, what I have done, you can make it into a theorem. Any question? Let's look at another example. So suppose you want to find this limit. Now this gives me an idea, because this guy is its limit is going to 0. So if I start use sandwich sandwiching, or I think we called it pinching theorem. So since I know, because I know that this limit does not exist. But that doesn't mean that the limit of the product cannot exist. It's even possible that the limit of neither of these exists, but the product may still have a limit. But I start with the sandwiching theorem. So I know that no matter what range I consider, sine is going to give me values between -1 and 1 +1. For all x, this is true. So all I do is multiply with this guy. Now this guy, this function, I should write it here. Notice that has a positive range. Because that's how it's defined. It's only defined for those values. Domain is when x cube plus x square has to be greater than or equal to 0. It's only defined for those values. But this means has to be greater than 0. Now, this guy, x square is, Zal, go away from here, is always greater than 0. And if the product has to be greater than 0, that means x plus 1 is greater than 0. That means x has to be greater than -1. So the domain is that's a good thing, because if we want to find the limit at a point, we need at least some small interval around it. So the domain now x cube plus x square sine pi over x is defined around an interval is defined on an interval x is equal to 0. Well, at least it's defined for this interval. Except that, because that we don't care. So we can at least try finding the limits. And the domain is this. And we know that no matter what number we give from the domain, the range is always positive. Because that's how you define it. You give it a positive number inside, and it's a positive root which comes outside. So that means if I multiply it by this, the inequality survives. Inequality remains same. Now all I have to do, now apply the sandwich theorem. The pinching theorem. So I have This is 0. And this is 0. So this implies that the function which is sandwiched between them at x is equal to 0 its limit is also 0. With practice, you kind of start, you don't have to do all of this. You can just argue like this. That this sign is remaining between -1 and +1. And if you take any number between -1 and +1 and multiply with this guy, which is approaching to 0, and this is approaching some number, not approaching, but gives some number between -1 and +1. So if you multiply any number between -1 and +1 with a 0, you're going to get a 0. So that's all you got here using more rigorous arguments. Now let's do some examples related to epsilon delta. So suppose you are given this. Limit x is equal to 0. Is equal to 2. Now if I consider .5, that means if I consider this range, x around 2, all those values of x around 2 is differ from 2 by 0.5, but are positive. Then what is the margin of error around the limit? Or what is delta such that f of x, which is this, -2 is within that margin of error. So we can just plug in and check what happens. So if I put in Ex, well, first of all, we need to know what kind of graph this function has. Around the value x is equal to 0. So 1 over x has this kind of graph. And e to the x has this kind of graph. At x is equal to 0, you have a 1. This kind of graph. And you are just shifting it over here. And around x is equal to 0, this is just increasing. And over here is negative times negative. So the graph of total function remains positive throughout this. So I can just put in the values and check what happens at these corners. So 1 over 2, 0.5 is 1 over 2 minus 1 over 0.5. So if I compute it on the calculator, which I'm doing right now on my other computer, then this gives me a value of 3.44. While this is at x is equal to 0. Well, this wasn't supposed to be minus 2. This was supposed to be 0. Because the limit is at 0. At x is equal to 0.5. So from here, I have x less than 0.5, but greater than minus 0.5, but x is not equal to 0. So I get 3.44. And at x is equal to minus 0.5, I get e to the minus half, which gives me minus 1. This gives me 1.26 up to 2 decimal places. So that means that this line between minus 0.5 and 0.5 is all mapped between 1.26 and 3.44, while my claim is that the limit is 2. So I have to choose a delta. So that the mapping remains within delta margin around L is equal to 2. So which one, how should I take? So this above it is by 1.44, while this below is 0.74. So it's clear that if I consider a bigger margin above here, like 1.45, it will cover things over here. So I can say choose delta is equal to 1.45. Then for this delta, epsilon is equal to 0.5 gives me if this is true, then f of x minus 2 remains within this margin of error. Now you can see that if I reduce this range, what happens? if I reduce epsilon to 0.1. So around 0, now I'm looking only at minus 0.1 and plus 0.1. So again, I can just compute and if I just plug it in my calculator, I get 2.21, while when I put in minus 0.1, I get 1.81. And my limit is at 2. So this is above by 0.21 and this is below by 0.19. So I can choose delta to be 0.22 and it covers both. And now you can see that the delta has shrunk. So this guy are now mapped to a smaller margin around it. So choose delta to be 0.22 and the limit L is equal to 2 is verified for this lambda and this epsilon. So all that it says is that if you have a small margin of error, there is a corresponding epsilon for which you will be mapped there. And you're just kind of verifying it here. Now, let's look at this one. Find the limit accurate up to 3 decimal places using computational method, using, let's say, a calculator. Well, first of all, we will have to believe that the limit exists, because when we do things with calculator, we might believe that we are getting a limit and it may not really be a limit. But just let's just assume that the limit is something over there. Then what I'm going to do, I'm doing this. Clearly putting in the value x is equal to 0 here does not tell me much. I have a 1 plus 0 and it's raised to the power of a nonsensical number. So I don't know what to do, but I can just start computing. So I can take a margin around x is equal to 0. So let's say 0 plus minus 0.1. So this small interval, and see where is it mapped using this function. It will be mapped in some range, and then I can try to figure out what is that range. Then what I'm going to do, I'm going to start making this margin around 0 smaller and see where is it mapped. So if this shrinks, and then I make it even smaller, and if this shrinks, so then I'm zooming in. Zooming in to the limit. So let's try this. So what I'm going to do is compute 1 plus 0.1 to the power 1 over 0.1, which is 10. So essentially 1.1 to the power 10. And that gives me, when I put it in calculator, 2.594. I'm rounding the calculator's answers up to the third figure because I want it to the accuracy third. And then I look at over here. So 0.9 to the power 10. And this gives me 2.868. So it's somewhere, the answer is somewhere over here. So what I try to do, well, I can do it in one leap, or I can do it in many steps. When I do this, I'm having 1 over, which is equal to 100. So 1.01 to the power 100. And that gives me 2.705. Similarly, and this gives me 2.731. So it was first in this range. I have narrowed down the range. It's somewhere between 2.705 and 2.731. There seems to be, no, it shouldn't be minus, yeah, it should be minus 10. Yeah, that's what I was doing. Taking the power to the 100 and inverting it. That gives me 2.731. Well, actually, it gives me 2. So 0.99 to the power 100. And then inverting it. So I can keep doing it. So for example, if I try 1 plus 0.0001, and over here, I will have 10,000. Similarly, 0.9999 to the power minus 10,000. When I plug in these numbers in calculator, I get over here 2.718, and this one also 2.718. That means that the range I'm narrowing it in, this differs by difference is less than So you don't see it at the third decimal place. And by these successive things, you can see that it's approaching some number. And if you look at this number, which is it is approaching, you can check that the value of E, it starts like this. So actually, this limit is what we call this number E. Whatever the limit you get, you can show that the limit exists, it reaches a number. Can't compute it exactly, it just keep adding and adding, you keep adding and adding more points here. But whatever that number is, that's the E. Should I do more? Let's do one more. So suppose you want to show using the definition of limit. Now, what you have is what we want is that for x minus 2 less than epsilon and greater than 0, you want some kind of this kind of thing coming out, greater than delta. For any delta such an epsilon, for any delta such an epsilon should exist. So we all the time we just try to first guess that what we can do. So I start from here and I know that 1 over x minus 2 is now gonna be bigger than 1 over epsilon, and I want to get this thing. Less than delta. So if I try to look at this inequality, I can write it like, because there's a absolute value which breaks up, and in the absolute value you can absorb the minus signs. So I want this kind of inequality. Delta in any case is bigger than 0. This breaks up. Now, if x is bigger than 1, I can remove it. Or I should say, let's do it this way. So I need something like this. So what I'm going to do, this gives me an idea that if I look in a small interval, around x is equal to 2, my limit point. Let's say I can consider this 1.5 and 2.5. And over there, I have to show this because that's all what matters. So in this interval, if I choose epsilon to be equal to, I'm just looking from here, 2, and if I choose a number which is bigger than these x's which I put in, then the inequality will become even stronger. So let's put in 4, just arbitrarily. A delta, something like this. Then for any x less than 8 less than epsilon, we have is less than A delta, because that's how we choose. We chose. Now, this A delta within this range this implies two x dot delta. And now I can do and that is obviously equal to 2, sorry, x minus delta. I didn't have to invert it here. It's 2 एक second यहाँ पे. So I have 2x x minus 2, which I can write as 2 minus x over 2x. So this gives me 1 over x minus 1 over 2. So I have proven that for any delta, there is some epsilon, so that you are mapped into this. These, by definition, proofs, they are kind of always very difficult, and you don't get much ideas beyond some simple things. But still, I just want you to do one example. Those numerical ones give you more idea that what's actually happening. We can do one more, or probably I'll just put them in the homework. Any question? Because I'm going to stop here. All right, then let's stop here.